And I did want to say something briefly about time standards. Um, so time study is what you do when you actually have a job that someone is out there doing, and they go out and you have someone go out and measure the length of time that person takes to do the job. But if you have a new job that needs to be done and no one's currently doing it, how do you get an estimate? Well, again, there is a whole science of time standards. People have done laboratory tests to determine how long it takes workers to do certain types of movements, certain types of activities. Here's these third legs again, those elemental motions that I talked about earlier. There's times associated with all of these third legs, like moving your hand a certain distance, lifting a certain weight a certain distance. All of those things have been timed. Right? And so methods time measurement, or MTM tables, time all these basic movements in what we call TMUs. And that's simply a time measurement unit. And 1 TMU equals 0.0006 minutes. So we're talking about a very, very small chunk of time. And one of the good things about doing this sort of analysis, as opposed to watching somebody do a job, even if it's a job that already exists, is that you avoid the Hawthorne effect. And you probably read about the Hawthorne effect in one of your general management classes. Basically, the problem is that when you watch somebody doing something, they change how they're doing it. And they might speed up, they might slow down, and it might be subconscious. They might not be trying to fool you or anything. It's just that it's hard to do something sometimes when you're being watched, or hard to do it naturally. So if you want to avoid that Hawthorne effect, or if you just don't have anybody currently doing the job, you can rely on time standards. So here I've got an example I pulled from an MTM table. How much time is it going to take to move an object to an indefinite location? So you're going to pick something up. It's going to be up to 2.5 pounds, and you're going to move it between 3 1/4 and 1 inch. There's a table and of course a computer program that would tell you that would take 2.9 TMUs, or basically 0.00174 minutes. So if you had an operation, you could break it down into these TMUs. You can basically calculate, break it down into these third legs and these motion elements. You can basically calculate how much time that operation would take. Well, time study works well for measuring work that is very repetitive, like assembly line work, or even for less repetitive work, but manually oriented work, where the worker is doing a task, working a machine or something like that. And what about less routine work, like office work? And you wanted to get an idea of what fraction of a person's workday was spent doing that type of non-routine task. For example, what if you were interested in the fraction of time that a professor spent in meetings during the week? How would you get a handle on that? What we can do is apply a technique called work sampling. So you give the professor a alarm clock, basically, and every X minutes you have to determine what X is based on how many observations you think you needed. The alarm goes off, and X is a random variable, so it's not a fixed interval, it's a random interval. And the alarm goes off, the professor writes down exactly what he or she is doing. So if the alarm goes off 100 times during the day, or say during the week rather, 100 times during the week, and 20 out of those 100 times the professor was in meetings, then you say that the percentage of time the professor spends in meetings is 20%. Now, it's probably not really 20%, though sometimes it seems like that to me. But the important thing here is understanding the illustration of how you do work sampling. It's for non-routine work, and you just try and get a handle on what fraction of the time a person is doing a certain type of task. And again, that time interval needs to be random. Just like when you're measuring more routine work for work sampling, it's key to figure out how many observations you need to gather, how many times that alarm needs to go off. Again, we're trying to figure out n the number of required observations, the maximum percentage error E you want to have in your estimate, and how much confidence you want to have in your estimate. And again, we're just going to take on faith right now that if I want to have 95.5% confidence interval, that implies a z-score of 2. And we do the same sort of thing. We basically collect some data. We have an estimate p of the fraction of time based on that initial sample of data that we collected. So in the example I just gave, it would be 20% is the fraction of time p that the professor was spending in meetings. If we want to be 95.5% confident of being within e of the true mean time, we set n using the following formula. So we're going to take z, which in our case here is going to be 2, we divide that by e, that maximum error, and square that and multiply it times p times 1 minus p. So it's a different formula than we were doing with time study, and the different formula is because it's a different random variable here. It's binomial here as opposed to being normally distributed, but we just can focus on what we're trying to do here and what the formula is. Suppose, for example, going back to our professor's example, we want to be 95.5% sure that our new estimate of the fraction of the time the professor spends in meeting is no more than 5% off the true mean. Our initial estimate was 20%, or 0.2, when expressed as a fraction. So there's our z-score. That's our maximum percentage error we want to be off by. There's our initial estimate of the fraction of time that the professor was spending in the meeting, and we do the math and we get 256. So we could require a lot of observations. We're going to have to record the professor's activities for another couple weeks if we want to get that many observations to justify our estimate of the professor's time that he is spending in meetings. Finally, I'd like to talk a little bit about the learning curve. The learning curve is based on a fairly common sense notion that the more you do something, the better you get at it and the faster you can do it. That seems like common sense, but it turns out that we can actually apply a mathematical model to that general principle that does a pretty good job of predicting the time required for a worker to perform a task at a certain point in the future. This phenomena was first observed, first observed and then modeled, I should say. People probably observed it before, but they didn't realize how easily it could be mathematically modeled during World War II during the production of Liberty ships. Liberty ships, of course, were ships that the United States produced, freighter ships, for convoying materials to Europe to stage in Europe for American troops and for our allies to fight in the war. So we made hundreds of these ships, and there were large, complex assembly processes, machining or fabrication and assembly processes involved, but it took a lot of time in each shipyard to make the first ship. But that time per ship quickly dropped as workers gained more experience making the ships, and people discovered that that drop in time per ship followed a neat mathematical formula, which made it particularly useful for predicting the time required to produce ships in the future, and of course how many workers you would need, and so forth and so forth. So the basic idea is that as cumulative production doubles, the time required per unit decreases to a fraction of the previous required time, and that fraction is called the learning rate. So for example, if I produce 1 unit of a product and it took me 10 hours to produce that first unit, to produce the second unit of the product, that's doubling my cumulative production, going from 1 unit to 2 units. And if I have a learning rate of say 90%, it should only take me 90% of 10 hours, or 9 hours, to make that product the second time. That seems overly simple, but actually this formula seems to work and is used in industry to predict time required to produce a unit of product into the future. So for our model here, let's just use a little notation. Big T with a subscript of n, that's the time required to make the nth unit. and I'll let LR be the learning rate, again that percentage, that fraction. So suppose that we've got a new assembly. It takes 10 hours to assemble the first unit. The learning rate of a similar product was 90%, so we're going to use that on our new assembly as an estimate of the learning rate. How long is it going to take to make the 25th unit? Well, I have a general formula here, okay, which we'll come back to in a second. If I go back to my graph here, here's that formula graphed, and again you can see the basic idea. It's starting out with the first unit that's taken 10 hours, and then as I make more and more units, by the time I get to the 25th unit, my time per unit has dropped to, it looks a little bit above 6 hours. Right? So the formula used to develop that curve is on this page. So again, here's my time for the nth unit. There's a time it took me for the first unit. I take that, multiply it times n raised to this power. So this power is a fraction here. And in both the numerator and denominator of the fraction is the natural logarithm. So ln stands for the natural logarithm. That's also a function, of course, in Excel. ln is a function in Excel, so you can find this in Excel. So the natural log of the learning rate, in our example that's 0.9, divided by the natural log of 2, that will determine the exponent that you raise n to that power, multiply that times the time to make the first unit, and that will give you the time to make the nth unit. So again, in our example, the learning rate is 0.9. It's a log of 0.9 divided by a log of 2. If I want to know what time it took me to make the 25th unit, I raised 25 to that power. That power ends up being negative 0.1520, and multiply that times 10, and I get 6.13 hours, which is pretty much what I see here on this graph as a time required to make the 25th unit.